The worksheet today, a few more related rate problems, and takes a little bit different direction, but it's still the same basic procedure. We've got to find some relationship between the quantities that we're dealing with. We've got to, well, figure out what rate, how that's going to be represented, and then go through the derivative and make the correct substitutions. In this case, and in some of the other problems, we're going to run into a relationship between similar triangles. Now, we haven't seen anything like that before, at least here in calculus, but you've probably dealt with similar triangles. But terminology, and especially this particular problem, the way it's worded, I wanted to kind of take you step by step through this and then get you going on the other problems. It says a man 6 feet tall walks at a rate of 5 feet per second away from a light that is 15 feet above the ground. When he is 10 feet from the base of the light, at what rate is the tip of his shadow moving? And then part B, at what rate is the length of his shadow changing? Now, you may look at that and think, well, that's the same question, but let's look at the details first of what we're actually trying to find here, and then we'll see how we go about finding that. Now, in part A, it says the tip of his shadow. So that's going to be at this point right here. How fast or what rate is it moving? First of all, which direction is it going? Okay, it's going to be going this way. And, well, are we going to be representing it as the shadow? What I just drew here is actually what we're going to be looking at in part B. So what do you think we'll be dealing with in part A? Let's go ahead and draw the triangle out and identify some parts so we can say it's X or Y or S or whatever we've notated this as. My nice straight lines there. Okay, so this would be the light, and so this part would be 15 feet. Here's the man at 6 feet. Okay, and this is going to be the tip of the shadow. We are told that he's going to be 10 feet from the base of the light. That represents what? From the right triangle, right angle part out to what? Okay, right here. Now, we're saying exactly the instant when that is 10 feet. So that's going to be changing with the problem. So we don't want to call that 10 right now, but let's call that, let's call it M for the position of the man from the light. So we're going to be looking at the particular instant when M is 10, but we've got a long way to go before we get to that point. Now, the length of the shadow is this right here. Let's go ahead and just call that S. And one other important part to this triangle would be what? Now we've identified parts of it, but as a whole, we need to look at the, I guess we could call it the base of the triangle, the entire base. And let's just go ahead and call that X. You could call it B, you could call it whatever you want, but this base of the triangle, we actually need to identify 3 parts. From the pole to the man, from the man to the end of the shadow, that would be our length of the shadow, and then because of similar triangles that we'll be dealing with here in just a second, we need to identify the long portion of the base of the bigger triangle. Okay? So, as we look back to our question, part A, what rate is the tip of the shadow moving based on the variables we've put on here? Part A, we're going to be trying to find what? One good guess would be the rate that S is changing, but that is actually, S represents the length of the shadow. That's actually going to be the question on part B. Part B, we're asking in terms now of our variables, what is ds by dt? Okay. How is S, the length of the shadow, changing? Okay. Now, part A is quite tricky here. When we look at just the end of the shadow, the tip of the shadow, we're really looking at how, okay, right, how X is changing. Okay. How is the length of X changing? And that's going to show us how fast that tip of the shadow is. So part A, we're really asking what is dx by dt. Okay. Okay, always good to figure out what the question is, what quantity we're trying to find, and sometimes that is pretty difficult. But very important to know what we're trying to find, so now we can focus in on what do we know and how do we find, how do we answer the question that we have. Okay. Now, also, this is kind of that problem-solving stuff we talked about last week, the optimization techniques. Okay, what are we asked about? What do we know? And then go through the procedure to answer the question. So we've done the first part. What are we wanting to find? And now the second part, which a lot of times is the hardest part. What do we know? How is everything related? Okay. And in this case, well, for the variables we've identified, there's actually a couple different equations, a couple different relations that we could look at. One, dealing with the height of the man and the height of the light, we could set up similar triangles. Okay? And what would be the equation for similar triangles here? What was that again?
X over 15 is equal to X over 6.
Okay, X over 15 is equal to S over 6. Yes, that is a correct relationship, a correct proportion with similar triangles. We're using the base of the big triangle over the height of the big triangle, and that's going to equal, and we've got to focus in on the smaller triangle, the base of it divided by the height of it. Now, sometimes we can look at position rather than, rather than the big triangle ratio equaling the little triangle ratio. Another way you could set this up is, and we're about to run out of room, but we'll show these two different equations and then move to the next page and work with it. We could say 6 to 15 is equal to, what would the other ratio be there? Okay, S over X. So two different ways, probably more ways than that, to represent these similar triangles, but either of these two ways would be good to work with. And let's see. Let's go ahead and choose this one. Which one's right? Which one's the best way to look at it? Well, that's personal preference. As long as you get a right proportion, doesn't matter which right one you do. Now, there's lots of ways to set up wrong proportions here as well, but make sure you get your relationships correct. Okay, so we'll use the x over 15 equals s over 6. And then one other relationship we'll be looking at, kind of just a very basic one that you may overlook here, but look at the base and how we're describing it. Very important relationship here. X is going to equal what?
M plus S.
Okay, the M plus S. So you might think, well, that's just so basic we don't need it, but yeah, we do need it with the information that we're given here. So let's see, next slide. We have our x over 15 equals s over 6, and we have x equals s plus m, or m plus s, whatever order you want to write that in. Okay. Now, we're also given in the problem some rates, or actually one rate, and then asked to find two others. In the problem, it said when the man is 10 feet from the light post. Okay, what did we say that represented with our variables? Okay. Our questions basically, what did we say? dx by dt equaled what? And part B, ds by dt equaled what? Now there is one other thing that we were told, and with our variables, the way we've represented things, what would that be? How would we represent that? The 5 feet per second is going to represent what?
The rate of change.
Okay, the rate of change of what? Which variable?
And the base of X.
Okay, it's going to be m. Okay, the man is walking at that rate away from the post, so that's how M is changing. The farther he walks, the bigger M is getting. So the 5 feet per second will be dm by dt. So again, lots of different relationships here, rates of different things, rates of change. Okay. Well, now at this point, we've got two equations. We've got a value for m and a value for dm by dt, but we're trying to find dx by dt and ds by dt. What do we need to do to be able to find the dx by dt and ds by dt? We will need to differentiate, take the derivative with respect to t. Which one do we do that on? Well, actually, that's kind of a loaded question there. We could do it to both of them, okay? Or I'll show you a couple different things. To make sure we have this represented, which equation has the m? X equals s plus m, so take the derivative of that equation with respect to t. That's going to give us dx by dt equals what? Now, the really nice thing about this relationship is everything is linear. All the variables are just to the first power, so when we take the derivative of it, there's no chain rule to have to worry about. The derivative of x is dx by dt. Derivative of s, derivative of m, it's just ds by dt and dm by dt. Yep, question.
What is dt again?
dt, we're technically taking the derivative of both sides of the equation by the variable t. T represents time, and in this case it would be in terms of seconds. So derivative with respect to time represents a rate of change, or you could say a speed, velocity, okay? And that's really what we're trying to find out. How fast is the, well, I guess dx by dt, how fast is the distance from the light pole to the tip of the shadow, how fast is it changing? And then ds by dt, how fast is the length of the shadow changing? Okay, so it's all rates, speed, okay? And that's why we do the derivative with respect to t, to be able to figure out a rate of change with respect to time. Okay. Now, we do not know dx by dt, and we also do not know ds by dt. So because of those two unknowns, we're not going to be able to answer the question just with this equation. But what else do we know that we have not worked with yet? We have this equation. Now, we could say, before we take the derivative of this, we could go ahead and solve this equation for one of the variables and substitute it into the other equation. X equals, well, 15s over 6. We could plug that into x. Or if you wanted to go the other direction, again, these problems have so many different ways to do them. We could solve for s. S equals 6x over 15. Okay. Or, technically, we could just go ahead and look at this equation, take the derivative with respect to t of it. And that'll give us a relationship between dx by dt and ds by dt. So the derivative of x over 15 with respect to time would be 1/15 times dx by dt, and s over 6, derivative of that, 1/6 times ds by dt. And from there, well, in part A, we want dx by dt. So let's go ahead and substitute. We'll solve for ds by dt and substitute it in here. Multiply 6 and that's our ds by dt. We know dm by dt, that was given as our 5. So our equation now can be written as dx by dt equals, well, ds by dt we just figured out was, what did we say?
6 over 15.
Okay, yeah, 6 over 15. And then dm by dt was our 5. So this equation will allow us to find dx by dt. Subtract 6/15. 1 minus 6/15. Well, let's see. That would be 2/5. That'll be a little easier. So 1 minus 2/5 would be 3/5. And then dx by dt, divide by 3/5, which could be multiplied by 5/3. 5 times 5/3 would be 25/3, and unit-wise would be feet per second. So 25/3 is what, 8 1/3? 8.333. Okay. Question? Okay. This is 2/5. So when we take 1 minus 2/5, we get 3/5. Okay. I'm doing a few things in my head here and might be a little too much. Sometimes we do too much in our head and then we make a little mistake, but okay. So the length of that triangle, the base of that triangle is changing at a rate of 8.33 feet per second, which also in our problem represents the rate that the tip of the shadow is moving, okay, at that particular time. Now, what about ds by dt? Well, we solved the equation. ds by dt is this right here, which again, 6 over 15 is our 2/5. So the length of the shadow is changing at a rate of, let's see, 25 over 5 would leave us 10 over 3 feet per second. So the length of the shadow would be changing at a rate of, what, 3 1/3 feet per second? Okay. So lots and lots of kind of little details here that we've got to be careful with. We're going to find relationships. Some of these problems will involve some similar triangles. These walking away or walking towards a light will have a little more relationship between the distance from the light post to the person, the length of the shadow, and then the sum of those two parts, like we saw here with X. And just a lot of little details that we got to look out for. So a little bit different type of problem, same basic procedure. Figure out what you're trying to find. Look at what you know. Find your relationships with equations, and then from there, be able to find the rates that we're looking for. Okay? Questions?